Hey guys, got another AP question for you. Actually, two small questions. Trying to cover all the areas. There's some parts that they really hit more in the multiple choice than in the free response. So doing what I can. Still working on the review PowerPoint of some of the topics that you guys sent me. The subjects that I have written down to review are rate laws and elementary reactions, periodic trends, and the photoelectric effect, which will take like 10 seconds because you don't really need to know much about that. But anyway, let's go ahead and get through these questions. Again, if you haven't done these questions on your own, you're wasting your time watching this video. Do the questions, see how you can do, and then watch the video and let me talk you through. So this one's from 2014. It's number 7, so it's a 4-point question. The half-life of catalyzed aspiration, blah, 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 is represented above, measured under various conditions, shown in the table below. So we've got a number of different initial partial pressures. We've got a couple of different volumes and then 2 different temperatures. And then we can get the different half-lives. And it's not surprising that the half-life only changes when we change temperature, right? Because remember, half-life is related, the half-life is equal to 0.693 over K. So it's related to K, and K doesn't change by changing concentration, which when you change the volume or you change the concentration or the partial pressure, you're changing concentration. But K isn't affected by those changes, but it is when you start changing temperature. So we're going to get a different half-life because we're going to have a different K. So the reaction is first order. Explain how the data in the table are consistent with a first order reaction. So whenever we're talking about half-life, we are always talking about a first order reaction. So you have to say something here like it has a consistent half-life, and therefore it has to be a first order reaction because a consistent half-life is associated with a first order reaction. You wouldn't find that with a 0th order or a second order reaction. Okay, so something about having a consistent half-life needs to be in your answer. And I don't know if you remember that, but we said that this equation is only true for first order reactions because those are the only ones that give you that proper half-life result. So that's only 1 point. You just say that one thing and you basically have it. Calculate the rate constant K. This is what I just showed you. We're going to rearrange that equation. So instead of the half-life being 0.693 over K, it's K equals 0.693 over the half-life. And in case you don't remember 0.693, it's right here on your equation sheet. So make sure you've got that when you take the test. But remember that in first order reactions, half-life and K are related very simply. If the problem gives you half-life or asks about half-life, right, it's a first order reaction. So we punch this in the calculator. I want the reaction at 350 kelvins. That's all of these. And so the half-life is always 100. So I don't even need a calculator for this. That's 0.693 over 100, and it's 100 seconds. And so that equals 0.00693, because that's just divided by 100. It's moving the decimal point 2 places. And the units for this is just the inverse of seconds, s to the -1, or 1 over seconds. And you need to have those units to get the point. Is the initial rate of reaction in trial 1 greater than, less than, or equal to the initial rate in trial 2? Justify your answer. So now we have to remember what the rate law equation is. Remember, we have the rate of the reaction is equal to K times the concentration. And since this is a first order reaction, this is going to be the concentration of cis-2-butene. And so this concentration changes between trial 1 and trial 2 because trial 1, it's 300, trial 2, it's 600. So this is going to be twice as big in the second one. So the rate is going to be twice as fast. Now, to justify your answer, you would want to write out this equation. You would want to show that in the second trial, there's twice as much cis-2-butene, and so therefore the rate is going to be twice as high. So remember this general equation, right? It's the rate is equal to K, and then we put in the reactants, right? Whatever the reactants are, and whatever their exponent is, if it's an elementary reaction, which we'll go through that again next week. The half-life of the reaction in trial 4 is less than half-life in trial 1. Explain why in terms of activation energy. So in trial 4, that's the one with the higher temperature. Everything else is the same as trial 1, but it's got a higher temperature. And so our half-life is much shorter, which means the reaction is happening much more quickly. It takes half as much time for half of it to go away. So we need to explain this as activation energy, though. So what we need to do is tie these numbers, tie this math to the particle level. Like I said, you're often going to be asked questions where you got to connect particle level, math, and in the lab, right? Those three things, you have to be able to connect them together. In this case, we're doing the theoretical, the math, and connecting it to the particle level. So activation energy at the particle level, we're talking about particles colliding. And at a higher temperature, they are moving faster, and so they are more frequently hitting with enough energy to make the reaction happen. And that's activation energy. Remember, the activation energy is how much energy they have to collide with to make the reaction happen. And if you're going faster, more particles are going to do that, so the reaction will happen more quickly. And you got to say something along those lines. You need to mention particles colliding and tie that to the reaction speed. All right, so that's 4 points for that first question. Not too bad. The second question is got 2 parts to the question, A and B, and each part is 2 points. Calculate the number of grams of MgOH2, molar mass, blah, 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 that is dissolved in 100 milliliters of a saturated solution of MgOH2 at 25 degrees Celsius. So MgOH2 has a K value, a KSP, its solubility of 1.8 times 10 to the negative 11th. So this is really small. I'm not sure if you remember how to do K of solution. It's kind of before we did all that stuff with acid and bases. So all we have to do is this. Remember, 1.8 times 10 to the negative 11th, that equals we need the concentrations of our products raised to their coefficients. So in this case, so we've got the magnesium. So MgOH2 is going to dissociate into Mg2 plus OH minus, but it's going to be 2 of those OH minuses because I've got 2 of them right there. So this is going to be squared. And so this is going to be x, this is going to be 2x squared. So remember, we use this 2 here. We use it 2 different times, once as the exponent, and then once in this 2x, because that's the relationship between these two values. There's twice as much OH. So don't get too hung up on that. Just remember this is the way it's done. So I do all this math, and I get 1.8 times 10 to the negative 11th equals, it's going to be 4x cubed. So I'm going to need my calculator for this one. Now, you're not going to get a problem like this on our actual AP exam this year where you have to use a calculator, but there are ways to fudge these numbers to make it so that you could do this math in your head. And I've shown you several of those. And that should get you x equals 1.65 times 10 to the negative 4th. So that's our x value. Now we have to use that to find the number of grams. So this is a 2-point question. I said that before. This is the first point, getting that right there. To get the second point, we have to figure out how many grams this is, because this is molar of the magnesium, which is the molarity of the magnesium hydroxide, because there's only 1 mole of magnesium in magnesium hydroxide. So this is how many moles we have per liter. So we've got 1.65 times 10 to the negative 4th moles in 1 liter. I want to get rid of that liters, so I have 0.1 liters. And then I also want to turn this into grams, so that means 1 mole is 58.32 grams. So I can do all this in one go, bust out my calculator, and I get 9.63 times 10 to the negative 4th grams. And I'm just looking, I've only got 2 sig figs in this, so I should be calling that 9.6 times 10 to the negative 4th grams. And this should probably be 1.7. This should be 1.7 times 10 to the negative 4th, because we've only got 2 sig figs. And like I said before, they don't really care a whole heck of a lot about sig figs on most of the problems. But you never know which one they're going to grade it on. But they had this on their rubric, not this. But they also had just 9.6 on their rubric. So, but these are the 2 values you have to get this right, or at least you have to set this up right. If you got the wrong value here and plugged it into here, of course, you would still get the right answer if you set it up properly and did your calculation properly. So the other 2 points on this 4-point question come from this part of the question. The energy required to separate the ions in magnesium hydroxide crystal lattice into individual magnesium ions and hydroxide ions, as represented in the table below, is known as lattice energy, which we've already talked about. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. So this is 2 points, 1 point here, 1 point here. So in terms of periodic properties, right, you have to say something about magnesium having a smaller atomic radius than strontium. If you look at where they are on the periodic table, strontium has 2 more electron shells, so it's much bigger. That's the 1 point in the term of periodic properties. And Coulomb's law, I don't know if you remember Coulomb's law, but we're talking about the charge times the charge over the distance squared. And there's a constant in there, but this is the strength of that force. The electrical force between them, either attraction or repulsion, is based on the strength of the 2 charges, Q1 and Q2, over the distance between those things. So in terms of Coulomb's law, you have to say, because magnesium has a smaller atomic radius, that means the distance between the 2 is smaller. And because you divide by the distance, smaller distance means bigger value for the force. So it's going to be a stronger attraction, right? So in terms of Coulomb's law, there's a stronger electrical attraction because the 2 objects are closer together because magnesium is smaller. And so that's why you have this higher lattice energy. That's why it's harder to break that up. So it's something that kind of summarizes all that I just said. And like that last sentence I said, I think would work. And so that's not too bad. That's 4 points on that question, 4 points for the first one. Hopefully you did well on those. If not, don't worry too much about it. We're going to keep practicing, keep up with it, keep doing it every day. Coming next week, a little review. If you've got any more ideas of things that you want to hit again, I'll probably just be pulling up the old PowerPoints and going through some of the key points of some of the more difficult parts. So make suggestions. Hang in there, guys. You're doing great.